Okay. So for number 51, the baseball, the wording of the questions is kind of funky. So the first paragraph for number 51 says a base runner heads towards first base with a speed of 20 feet per second. A baseball diamond is a square 90 feet on each side. Okay, so that's our given information. Part A doesn't even require calculus to answer. Part B, we're going to end up coming up with the formula for dy over dt, which represents the rate of change of the distance from the umpire that's on third base to the runner. And then part C is wanting you, that question, like based on looking at what their answer is in the textbook, that question is asking you to use part B. So use the formula that you come up with in part B in order to calculate the runner's rate of change of distance from the umpire. The thing is, in part C, they word it as what is the runner's speed when he arrives at first base? To me, that sounds a lot like what the given information is, right? Like in that paragraph, it says a base runner heads towards first base with a speed of 20 feet per second. So the answer for part C is not 20 feet per second. The wording there is bad. And what they're really wanting you to do is to use the formula you come up with in part B. So question A is asking how long it will take for the runner to reach first base. To answer that question, you can use the distance equals rate times time formula, because you know the distance that the runner is running is 90 feet. So you can plug that in for D. The rate at which the runner is running is 20 feet per second. And you're solving for T there. So if you divide by 20 on each side, you end up with T is equal to 9/2. Or you can write that as 4.5 seconds. So assuming he's running at that constant rate of 20 feet per second, it would take him about 4.5 seconds to get from home to first base. Are we okay with that? Great. Okay, so B requires us looking at the picture. We're trying to find dy over dt, and they give us the hint to use the diagram in order to come up with the relationship between x and y. X represents the distance of the runner from home. Y represents the distance of the runner to the umpire. And then we know that each side of the baseball diamond is 90 feet, right? The distance between each of the bases is 90 feet. So do we see that? I'm sorry, Matthew, I'm going to step away from here for a second. Do we see that this ends up being a right triangle problem, where this leg of the right triangle will be constant, it will be 90, meaning that 90 can get plugged into our Pythagorean theorem equation, because as time is passing, that value is not going to change, but the x and the y would be changing. So we can set up our equation as x squared plus 90 squared equals to y squared. And then we're ready to differentiate with respect to t. So make sure you're showing the step that you're differentiating each term with respect to t. when we are differentiating with respect to t, using implicit differentiation. When we use implicit differentiation, we're thinking chain rule. And I realized that I was not the person to teach you guys chain rule. So I don't know what it is that you are saying to yourself when you're doing chain rule, if it's the same as whichever teacher you have. So I just wanted to briefly review. We use chain rule when we think about having a composite function. So if you have a function where you can think of having a function on the outside and then a function on the inside. Kind of like, I always think of the Russian nesting dolls when I think of composite functions. Okay, so you can think of a given function or given term as an outside and an inside. Then the derivative of that function would be the derivative of the outside function. You would leave the inside function alone, and then you multiply by the derivative of the inside function. Another thing I like to stress when I'm teaching the different rules of differentiation is that another way to read dy over dx, right, which dy over dx is the same as y prime, is the derivative of y with respect to x. And you guys used those basic rules of differentiation whenever you had y equals to a rule, where everything on one side of the equation was in terms of x, the independent variable, right? Or then y depends on what x is. So when you differentiate and you find the derivative, you're coming up with a formula that will tell you how y is changing with respect to how x is changing. When we differentiate an equation with respect to t, we're deriving an equation that will allow us to see how a variable is changing with respect to how time is changing. So to differentiate using implicit differentiation, the x squared term, I think of the exponent of 2 as being the outside function and the x as being the inside function. So the exponent of 2 is the outside, the x is the inside, right? Outside, inside. The square is the outside, x is the inside. So to take the derivative of the outside, I would bring the 2 down and I would subtract 1 from the exponent. Then I leave the inside alone and I multiply by the derivative of the inside. So the derivative of x with respect to t can be written as dx over dt. Do we follow that? Okay. The derivative of the constant is just 0. And then to differentiate the y squared term, again, I'm thinking of the exponent of 2 as being the outside function, y as being the inside. So bringing the 2 down, subtracting 1 from the exponent to differentiate the outside, leave the inside alone, and then multiply by the derivative of the inside with respect to t. So the derivative of y with respect to t. And then for the related rates problems, then it's just plugging values in that you know. For part B, they're not giving us, the question is not giving us a when we want to find dy over dt. So they want us to isolate dy over dt, but they haven't given us any information to describe the moment in time. So they just want the formula. What we can plug in is the runner's speed as they're heading towards first base. And they've kind of labeled it in the picture. But we're going to interpret that 20 feet per second as the rate at which x is changing. So dx over dt equals to positive 20 feet per second. And I'm using the positive 20 because as time is passing, x would be getting larger. So I'm able to plug in the 20 in for dx over dt and then solve for dy over dt. It's up to you. Your work, your steps might look different from mine. Like you may be able to do some of this algebra in your head, and that's fine. But basically you're going to divide by 2y on both sides. So you end up with dy over dt equals to 20x over y. I'm going to pause there for a second before I do part C. Does anyone have any questions? Matthew, make sure you unmute yourself and ask a question if you have one too. Okay. So like I said, the wording in part C is funky, but what they want to know is what is the runner's rate of change of distance from the umpire when he arrives at first base. So basically find dy over dt when x is equal to 90 feet, right? Because going from home to first base, he would have traveled 90 feet. We also need to know what y is at that moment in time. So we would go back to our Pythagorean theorem in order to solve for y. So plugging 90 in for x, I believe we end up with y equals to 90 root 2. If you simplified it to that. So y would be equal to 90 root 2 feet. And then plugging 90 in for x, 90 root 2 in for y. Yes. The 90s cancel, so we end up with 20 over root 2, which is the same answer that they have in the textbook, but they rationalize the denominator. I'm not really that concerned with it, but that does simplify to be 10 times root 2. For units, since y is being measured in feet and time is being measured in seconds, would be feet per second. And then we should summarize with a sentence. So we could say something like the runner's rate of change of distance. I'm just restating part B. The runner's rate of change of distance from the umpire. Oh no, I didn't mean to do that. There we go. Is 10 root 2, or if you wanted to use the decimal approximation, that's fine. It's 10 root 2 feet per second when the runner arrives at first base. what I think I want to do, I want to move on to the tracking rocket example next. If you still have questions about either of the other two problems, well, I just went from 18% to 13%. Okay, you plug in. If you guys have any questions on the remaining two problems, you can ask me about them when I let you guys get started working on related rates practice number 3. So I'm going to switch over to the notes. And we are on the tracking a rocket example, the last example from our related rates notes. And just let me grab Okay, so I told you guys the last time I put examples into this lesson that expose you to different types of common related rates problems. So this is another one of them. This problem requires trig. Okay, are we ready? So I'm going to do my best to draw a picture of the situation. So the first sentence says, a spy uses a telescope to track a rocket launched vertically from a launching pad 6 kilometers away. So here's the ground. Here is the spy. Here is his or her, whoever they may be. This is their telescope. And then we have the rocket, which is shooting into the air. Going up, up, up. Important to put the flames. Okay, so can we all kind of imagine this situation? So let's think about their tracking, just to simplify this a little bit. I am recording. Thank you for reminding or checking though. I think I'm recording. There's a little red button flashing, so I think so.
I don't have my license, so I can't. Does it stop?
Let's hope.
Okay.
Otherwise, I'll just make a different screen cast. It's not a big deal. Thank you for checking. So let's say that the telescope is like tracking the very top of the rocket or some point on the rocket. Oh, and then the distance between the telescope and the rocket launch pad is 6 kilometers. So at a certain moment, the angle theta between the telescope and the ground is equal to pi over 3 and is changing at a rate of 0.9 radians per minute. So this angle right here, we're calling theta. Now, theta is just a variable. We often name angles with Greek letters, but it's the same thing as like if you wanted to call it angle X or angle Y. It's just a variable that represents a quantity that is changing. There are some other quantities on here that we could think of as changing as time is passing as well. One would be the distance between the rocket and the telescope. We could use a different variable to represent that. I'm going to use Z. And then the height of the rocket off of the ground or off of the launch pad would also be changing as time is passing. That second sentence is describing the moment in time that we're going to end up answering this last question here. But it's also giving us our given rate. So d theta over dt, the rate at which the angle theta is changing, is positive 0.9 rads per minute or radians per minute. The last sentence describes the rate that we are solving for, which is the rocket's velocity at that moment. So at the moment when theta is equal to pi over 3, we are going to solve for the rocket's velocity. How could we write down the rocket's velocity? So the velocity is how fast the rocket is traveling and in what direction, right? Thinking back to 9th grade physics, velocity is a vector quantity.
dy.
Thank you, Matthew. dy over dt. So if you're thinking back to 9th grade physics, right? Velocity is a vector quantity, so it has both magnitude and direction. The magnitude would correspond to the speed of the rocket, and then the direction will end up being indicated by plus or whether we get a positive or a negative value to represent the velocity. So velocity, based on this picture, is going to be the rate at which the rocket, the distance of the rocket from the ground is changing. We can use that to describe the velocity. So like Matthew said, we're trying to find dy over dt when theta equals to pi over 3.
Is dy over dt like not the velocity thing, it's like a time thing?
It's dy over dt represents the rate at which the distance y is changing, which would be the velocity of the rocket. Just thinking about the situation as time is passing, so after the rocket gets launched into the air, y would end up increasing, z would end up increasing, theta would end up increasing as the rocket goes up, up, up. Now our given rate is d theta over dt, and we're trying to solve for dy over dt. So the relationship that we are trying to come up with next, right? We've stated our given, what we're trying to solve for, we need our equation. The equation that we come up with should relate theta and y. we actually don't want z to be in our equation because we don't want to end up with a dz over dt, which is a rate we know nothing about and we're not solving for. So our goal is to relate the y and the theta. And then we're given the distance between the telescope and the launching pad. So this is a right triangle, but an angle is involved. So we're not using Pythagorean theorem here. We would get stuck if we tried to use Pythagorean theorem because, like I just said, we know nothing about the rate at which z is changing, and we're given no information about z. So we're going to fall back on good old SOHCAHTOA.
So.
Just a little refresher on SOHCAHTOA, right? It's from right triangle trigonometry, and it's based on the angle that you care about or that you're solving for. The outputs of sine, cosine, or tangent are ratios of sides from the right triangle. So like sine of theta would be equal to the side opposite over the hypotenuse. Cosine of theta would be equal to the side adjacent, which is the side next to the angle, not the hypotenuse, over the hypotenuse. And then tangent of theta would be the side opposite over the side adjacent. So any thoughts on which of these we would want to use to come up with our relationship between y and theta?
Well, you mark tan because you know what the adjacent side is, but if you want to find the average.
Yeah, we want to use tangent, so we would have tan of theta is equal to the side opposite, which is y, over the side adjacent, which is 6. We end up what? Ooh. I need to highlight that. We want to use tangent here. If we had been wanting to solve for dz over dt for some reason, then we would have wanted to use cosine, because cosine would have been side adjacent over the hypotenuse. This is just my preference. So this is the equation that we're going to differentiate. I'm going to multiply by 6 on both sides. You don't have to do this, but I prefer to do this. So to rewrite the equation as 6 tan theta equals to y. So that when I differentiate with respect to t, I'm going to pull the 6 out on the left-hand side. And show I'm differentiating with respect to t. Okay, we had stated our given rate, the rate we're trying to solve for. We have our equation. We're ready to differentiate and derive the relationship between the rates of change. Rafi. Sure. I'll post the video, so if you did need to go back. That's okay. Okay. Are there any questions up to here? Are you guys talking because you have a question?
No.
Okay, well, let's differentiate then. To differentiate the tan theta, we're going to think of tangent as the outside function right? We're thinking chain rule. Tan is the outside, theta is the inside. The 6 is just a constant. It's going to be hanging out there. So thinking derivative of the outside tangent, what's the derivative of tangent? Secant squared. We leave the inside alone, which is the theta. And then we multiply by the derivative of the inside with respect to t, which would be derivative of theta with respect to t. So d theta over dt. And then the right-hand side of the equation ends up being dy over dt. Because it's 6 times tan theta. If it were 6 plus tan theta, where you were thinking about differentiating the 6 by itself, then the 6 would become 0. It's like if you were differentiating 6 times x squared, that would become 12x. So the 6 is like a coefficient there. So once we've differentiated, we're ready to plug in values. We have d theta over dt is 0.9. And we have theta is equal to pi over 3. Now, for this particular problem, we've been given theta. I'm going to flip this around. So we'll have 6 and then times secant squared of pi over 3 times 0.9. Just so that this, I'm going to put extra grouping symbols there just so it doesn't look like the pi over 3 is times 0.9. That's secant squared of pi over 3 times 0.9. Now, each step here for simplifying, we've technically represented the exact value for dy over dt, which the units on dy over dt will end up being kilometers per minute, because distance is being measured in kilometers based on the distance of the telescope to the launching pad. So it'll be kilometers per minute. I don't know about you guys, I can't wrap my brain around what that value is. So to me, it would be easier to simplify. To simplify by hand, so without using a calculator, you would need to use, well, actually, no, you wouldn't need to use an identity. But if you want to use a calculator because you're like, I'm a little rusty on my unit circle, we would need to use an identity to rewrite, because there's no secant button on your calculator. There is a cosine button though. And if you remember, secant is the reciprocal of cosine. So if you wanted to type this into your calculator, the way that you would do that is by pulling that exponent outside of the grouping symbols and rewriting the secant of pi over 3 as 1 over cosine of pi over 3. And you would also want to make sure that your calculator is in radians. So you would hit the mode button and make sure that you're in radians. Mode. And then make sure radians is highlighted. Or you are a unit circle pro and you go, oh, cosine of pi over 3 is 1/2. So 1 divided by 1/2 is just 2. 2 squared is 4. So that's actually 6 times 4 times 0.9, which ends up being 21.6. And I think that number is a little bit easier to kind of wrap your brain around for an answer. So we could say that the rocket's velocity is 21.6 kilometers per minute when the angle between the telescope and rocket is pi over 3, or something like that. I think I started to talk about this and then like lost my train of thought. Going back up to here to our derivative, we were given theta. You're not always for these type of problems given the angle to describe the moment in time. Sometimes you would be given information instead about z instead of the value of theta at that particular moment, or some other piece of information where then if you had to still solve for dy over dt, you would want to determine what secant of theta is based on the sides of the right triangle that's there, right? Like secant would be hypotenuse over adjacent. So you would want to know what those values are. And I think in this third related rates assignment, I think you do have to do that instead of solving for what theta actually is. Okay. I'm going to let you guys start working on that third assignment. If you have any questions from the last assignment, implicit differentiation, anything related to what we're doing, go ahead and ask me. I do recommend taking a look at this before you come to class next time because it will be due. There's a hard deadline at the end of the period. Okay. So